Picard here with another geometry video. Today we're talking about the Pythagorean Theorem. Many of us by now are familiar with the Pythagorean Theorem. Maybe we've used it. Maybe we've seen it used in the context of the distance formula. But here today we're going to explain it and extend our use of it just slightly. What is the Pythagorean Theorem? The Pythagorean Theorem states that in a right triangle, the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. There's a mouthful. Let's talk about what that means. First of all, some terminology. In a right triangle, the longest side is always called the hypotenuse. So in this case, C represents the hypotenuse. You can always find the hypotenuse opposite the right angle. It will always be opposite the right angle. The other two sides are called the legs indiscriminately. A, B, they're both legs. Doesn't matter which one's longer than the other. They're both called legs. So what does this theorem say? It says that if I take and square B and square A and add those two squares together, that sum will be equal to the square of C. A squared plus B squared equals C squared. Let's take a look at the proof. To prove the Pythagorean theorem, let's just start with a right triangle, just some right triangle, such as this one here. For our purposes, we'll just go ahead and label the lengths of the sides, A, B, and C, being sure to label the hypotenuse C and the two legs, A and B. Notice these are not the names of points. I've placed lowercase letters here as variables. These are not the points, not the vertices. These are variables that represent the lengths of the sides. The next thing we'll do is we will take that triangle and we'll actually copy it so that we have four triangles just like it. All identical, they're congruent triangles. I use the copy and paste function here from the Paint program in Microsoft. The next thing I'll do is rotate three of the triangles. I'll rotate one 90 degrees, one 180 degrees, and one 270 degrees. So they look like this. Now I'll move the triangles around to rearrange them just slightly. And we can begin to assign some values to some of the important measurements in here. For instance, each of these long sides is a hypotenuse of the individual triangles, which means the length of each of those sides is equal to C. Also, on the inside here, we find a square. Now, we might ask the question, is that definitely a square? The answer is it definitely is a square. First of all, each of these is a right angle. It's a right triangle. So we know we have four right angles here, and therefore the supplement to each of those is also a right angle. So this is a rectangle. And because each of these sides of the square, which I've called it, is equal to the long side here, A, this A, minus the short side, B, those are all congruent, so it is indeed a square. We need to know the length of the sides of the square, and so I think you can see that the length of this segment here is actually A minus B. So let's just go ahead and write that down. So this is A minus B. And this is A minus B. Okay, we're ready to do some work on this now. We can see that the area of the large square is equal to C squared. We know that because the area of a square is equal to the square of the sides. And since the sides of the square are equal to C, then the area of the large square is equal to C squared. What about the area of the small square? The area of the small square is equal to A minus B squared. Now you may remember back from algebra that the square of a binomial would yield the following: A squared minus 2AB plus B squared. And so we find that the area of the small square is A squared minus 2AB plus B squared. Now we also have these triangles. We need to pay attention to those triangles. And each of the triangles has height. The formula for the area of a triangle is area equals 1/2 base times height. Each of those triangles has base equal to B, you may remember. Now that's not the same as this B. The B I've just put in there as a variable saying how long the base is. And then H is actually A. So it's 1/2 BA. 1/2 B, if we were to draw the triangle, times A. There we go. So now we ask the question, well, how many of those triangles are there? There are 4 of them. So the area of the triangles, plural, is actually equal to 4 times 1/2 BA, which is quite simply 2 times BA. So that's the area of the triangles. Now, there's a rule in geometry that says essentially the area of some object, any sort of two-dimensional object, its area is made up of the individual areas of the figures that comprise it. In other words, if we can add up the areas of the triangles and the areas in the area of the small square, then we'll have the area of the large square. So what we're going to do is add the area of the small square to the areas of the triangles and see what we get. Area then is equal to a squared minus 2ab plus b squared plus 2ba. Now, you can see that I have these two terms, 2ab and 2ba. The 2ba, of course, can be rewritten through the commutative property of multiplication as 2ab. And you can see that 2ab minus 2ab is actually equal to 0, so those cancel. So what do we end up with? We end up with area is equal to a squared plus b squared. So the composite area of this figure is equal to a squared plus b squared. We also happen to know, because it's a square, that the area is equal to c squared. Therefore, we can say a squared plus b squared, the total sum of these shapes, is equal to c squared, the area of the large square. That is a proof of the Pythagorean theorem. There are actually hundreds of proofs of the Pythagorean theorem. That's one. It may be a good idea if you want to get a very firm understanding of it to find another one and just sort of work through it. Next thing we need to talk about are these values called Pythagorean triples. Pythagorean triples really are just useful. They're convenient to know in a classroom setting because a lot of times teachers and the people who write math problems on standardized tests will use Pythagorean triples because they make for nice, clean answers. And so knowing them will save you a lot of time. It says a Pythagorean triple is a set of non-zero whole numbers, a, b, and c, that satisfy the equation a squared plus b squared equals c squared. In other words, when we use the Pythagorean theorem, lots of times we end up with decimal values. Occasionally, depending on the numbers, we will have 3 numbers that are all whole numbers. For instance, 3, 4, 5. That's a Pythagorean triple. Why? Because 3 squared is 9, 4 squared is 16, 5 squared is 25. And when you add 9 plus 16, you get 25. 25 equals 25. So it's a Pythagorean triple. In other words, there's a right triangle that has these sides, 3, 4, 5. The reason that's so convenient is that if you see a problem involving a right triangle, and you recognize that it is involving a Pythagorean triple, you can very quickly identify the third side without really doing much math. You just notice that's 3, 4, 5, and you put in the 3, depending on which side happens to be missing. Or maybe you see that it's a right triangle and it has sides 3 and 4, legs 3 and 4. Well, you know the hypotenuse must be 5, 3, 4, 5. Okay. There are others such as 5, 12, 13. There's a whole bunch of different sets as we sort of go forward. This one, 3, 4, 5, is the most basic. It's the only one that involves consecutive integers, consecutive whole numbers. And so in that sense, it's the simplest. Next thing we need to be aware of is that if we multiply each number in a Pythagorean triple by the same factor, the 3 resulting products also form a Pythagorean triple. So for instance, we have this Pythagorean triple 3, 4, 5. If we multiply each of those numbers by 10, we have 30, 40, 50. That's a Pythagorean triple. If we were to multiply each of these original numbers by 2, we would get 6, 8, 10. That's a Pythagorean triple. If we multiply by 3, we get 9, 12, 15. Also a Pythagorean triple. So recognize those numbers. Again, it will save you time as you work through problems. Pythagorean triples and their multiples. Now that we know and are familiar with the Pythagorean theorem, we want to try to use it to accomplish some other things. So for instance, calculating the area of an isosceles triangle. Knowing the Pythagorean theorem can make that a lot easier. You'll note, first of all, that every isosceles triangle can be divided into 2 congruent right triangles. What we need to do to accomplish that is draw in the altitude the vertex, like this. And when we draw in that altitude, we know it's at right angles. And you can see that that altitude divides the isosceles triangle into two right triangles. So when we look at the right triangle, let's just focus on the right triangle on the right side. Once we have that right triangle, we can use the Pythagorean theorem to calculate this height. How do we do that? First is to recognize that when I draw in the altitude, I've bisected the base. So this is now 7, and this is 7. And at this point, we'll use the 9, which is the hypotenuse over here, and the 7, which is one of the legs in this right triangle, to calculate the height. So we know that the height squared plus the 7 squared is equal to 9 squared. A quick tie back into algebra. Remember, when you take the square root of a number, you're always dealing with the positive and the negative value. There's always a plus and a minus. But when we're in geometry, because distance is always positive, we only need to worry about the positive value. So the square root of 32 ends up being, for our purposes, we'll just put this in simplest radical form. And so we know that there's a 16 in there. We need to factor that out. It becomes 4 square root of 2. And we'll just leave it in that form for now. So the height of this triangle here is 4 square root of 2. Once we know the height, we can calculate the area. You'll notice this formula here in parentheses says area equals base times height. Now this is very dangerous. Please pay attention. That is not the formula for the area of a triangle. The formula for the area of a triangle is area equals 1/2 base times height. But there's a couple ways we can go about this. We are dealing with two different triangles. We've dealt with this triangle on the right to find the height. We are ultimately trying to find the area of the whole triangle. If I want, I can go forward with this formula. Area equals base, which is 7, times height, which is 4 square root of 2. I'm still working in the context of the small triangle, but I'm going to find the area of the large triangle. Why does that work? Because I've divided my base in half. My base is actually 14. And so when I've done that, I've actually taken into account that 1/2 already. It's a bit of a shortcut. I don't necessarily recommend you take it unless you're very confident with it. Otherwise, we'll talk about how we get back to this and use that one. Using the shortcut, we can see that the area of the larger triangle is equal to 28 square root of 2. How would we sort of walk on safer ground and use this formula, the one we're more familiar with? Well, to do that, we'd have to revert back to the larger triangle. So we know that the area would be equal to 1/2 times the base of the larger triangle, which is 14, times the height of the larger triangle, which is 4 square root of 2. And of course, 14 times 1/2 is 7, times 4 is 28. We end up in exactly the same place, 28 square root of 2. Note that the height of the small triangle on the right, this height right here, is the same height as the larger isosceles triangle. H is the same in both of those, so that's something to be aware of. The last thing we need to look at is called the converse of the Pythagorean theorem. And the converse of the Pythagorean theorem helps us answer the question, are we looking at a right triangle? The converse says that if the square of the length of one side of a triangle is equal to the sum of the squares of the lengths of the other two sides, then the triangle is a right triangle. So for instance, suppose we're looking at a triangle like this. And we know that the triangle has measurements 14, 12, and 5. And we're trying to answer the question, is this a right triangle? To answer the question, we simply square the 14, and we ask whether that's equal to the sum of 12 squared plus 5 squared. So we end up with 196. Is that equal to 144 plus 25? I think you can see 144 plus 25 is actually equal to 169. So these are not equal. What does that mean? It means that this is not a right triangle. Okay, so we use the converse of the Pythagorean theorem just to identify right triangles when necessary. Those are the rules associated with the Pythagorean theorem. Make sure you work through a few practice problems. And as always, if you have any questions, send me an email.